This is our first problem. So we have a hole, small hole in a very big infinite plate, which is subjected to these tractions at the remote ends. The horizontal remote ends, that is this one and this one, are stress free, traction free, whereas the remote ends, the vertical remote ends, have traction. It is very easy to find. So now you note that del vu is not there. So the whole boundary is del vt, and on these boundaries we have the normal. For example, this boundary, we have the normal is 1 0, and t bar is sigma naught e1, which means that t bar 1 is equal to sigma naught, t bar 2 is equal to 0. So if you now apply the Cauchy relation, which is t on this boundary here at this point, t I bar has to be equal to sigma ji and j, you will get t1 bar is sigma 1 1 n1, n1 is 1, and sigma 2 1 n2, n2 is 0. So sigma 1 1 has to be equal to sigma naught. If you do it for t2 bar, you will see that sigma 2 1, t2 bar has to be equal to sigma 2 1, but t2 bar is 0, so sigma 2 1 has to be equal to 0. If you do it on this boundary, the normal is minus 1 0, but t1 bar is minus sigma naught, t2 bar is 0, and if you do the same exercise, if you use this expression for a point here, you will see that the boundary conditions here are the same as on the right edge, which is sigma 1 equal to sigma naught, sigma 1 2 is equal to 0. Okay, so let me erase this. So as we go far away from the hole, in other words, as r tends to infinity, we must have sigma 1 1 equal to sigma naught, sigma 1 2 equal to 0 for this problem. And then it's easy to see that if I take a phi to be of the form, let's say sigma naught x2 square by 2, then that phi will satisfy this. How I do del phi del x2, it will be sigma naught x2, del square phi del x2 square would be sigma naught, and this is equal to sigma 1 1. So sigma 1 1 equal to sigma naught is satisfied by Airy stress function of this form. That much is clear. Now we are going to solve this problem in Cartesian, not in Cartesian coordinates, but in cylindrical polar. So we just replace x2 by r sine theta whole square by 2. So this term must be included in the Airy stress function, and then you get r square sine square theta, which you can convert into something 1 minus 2 cos 2 theta or something, because our other terms in that are going to come from the Fourier series are going to contain powers of cos n theta. So it is good to convert this square of a trigonometric function into a multiple of the angle. So we are going to convert sine square theta into cos 2 theta, and when we do that, so this will be the part of the Airy stress function which goes to sigma 1 1 equal to sigma naught as r tends to infinity. So this has to be included. What else has to be included? So uh, to figure out what else has to be included, we go back to the table. Okay, this is the table that we looked at in the previous lecture. Now we know that the stresses have to lead to sigma 1 equal to sigma naught and sigma 1 equal to 0 as r tends to infinity, and this part is going to do that. This part is going to do that. So whatever else is there in phi has to lead to stresses that go to 0 as r tends to infinity. Okay, so now we go back to the Mitchell table and figure out which terms give us stresses so that both sigma, all the stresses go to 0 as r tends to infinity. Okay, so one term is, let's say, this. It has minus r square in sigma r 0 and 1 by r square in sigma theta theta. Okay, so this goes to 0 as r tends to infinity. Then what about this? This also goes to 0 as r tends to infinity. Then we have these terms don't go to 0. This goes to 0 as well. And this actually does not go to 0. This is r by sine theta, so that we have to figure out what it goes to. But then there are other terms here. So for example, this one for n equal to 2, this goes to 0 as 1 by r square, right? And then you have this one, which for again n equal to 2, this will go to 0 as r to the power 4. Okay, there may be other terms that go to 0 as r tends to infinity, but we are going to include these 4. So there is a limit to the number of terms that we can figure out. I'll come to that in a moment. So we have chosen 4. One is log r, one is just theta, one is 1 by r square cos 2 theta, and the other is r to the power 0 sine 2 theta. So with those terms added, this is your resultant Airy stress function. These constants are unknown. This is the term that gives you the stress state as r tends to infinity. And these are terms that are going to give you stresses that are active close to the void and inactive as you go far away from it. Okay, now I have 4 constants here. I have chosen 4 terms. I could have chosen more, but I chose 4 terms because there are 4 boundary conditions that I have left. And from those 4 boundary conditions, I can determine only 4 constants. So I have to choose 4 terms. I could have chosen something else, but then I was sort of motivated by the fact that there's a cos 2 theta here. So I got a bit biased and chose these 2 theta wala terms. Okay, now I could choose this log r as well. And now from this I can determine the stresses. These are the stresses. These are just determined by taking derivatives of this and plugging it into these equations. I determine the stresses. The stresses also contain ABCD. These also contain ABCD. And now I have to determine this ABCD. How do I do that? So to do that, you will now see why cylindrical polar is a good coordinate system to choose for this problem. So let us go back to this and try to figure out what is the boundary condition on the hole. So on the hole, the normal is this, and the normal in the cylindrical polar coordinate system is minus ER. So if you work now in the cylindrical polar coordinate system, the stress state at the hole, say at a point this, is T1 bar equal to sigma RR NR plus sigma R theta N theta, where N theta is 0, this is minus 1. T1 bar is 0 because this is a traction free hole, which means that at this point sigma RR has to be equal to 0. Similarly, T2 bar is equal to 0 on the hole, and it is equal to sigma R theta NR plus sigma theta theta N theta. This is 0, N theta is 0. This is minus sigma R theta. T2 is 0 because this is a traction free hole. It means that sigma R theta is also equal to 0. So what I have here are these boundary conditions at the hole, which gives me that sigma RR and sigma R theta is equal to 0 at R equal to A. If I had worked here in the Cartesian coordinate system, I would have got a more complicated boundary condition. I would have actually got sigma 1 1 cos theta plus sigma 1 2 sine theta is equal to 0 at R equal to A, and then another equation for sigma R theta. So this would have been a more complicated equation because in the Cartesian polar coordinate system, n1 would have been cos theta, n2 would have been sine theta, and that would have led to a more complicated equation for the Cauchy condition. Whereas in this case, because the normal is in one of the coordinate directions, that is minus ER, I get this right away. Okay, so now we go back to this and we have sigma RR and sigma R theta equal to 0 when R equal to A. So we put R equal to A here and 0 on the other side. So we, for example, 0 equal to sigma naught by 2 plus sigma naught cos 2 theta by 2 plus A by so this requires that the constant terms are 0. So this and this, the sum of this and this are 0. Then the cos 2 theta terms are 0. So this leads to the first one, sigma RR equal to 0 at R equal to A, leads to this. Sigma R theta at R equal to A leads to this. Okay, and then cos 2 theta sigma RR at R equal to A leads to this, and sine 2 theta leads to this. So we can solve for, we have 4 equations, solve for the 4, and these are the constants that we get, which is why we started with 4 constants. We started with 4 terms. We could have taken more, but then if we did not have boundary conditions to solve. So all the necessary boundary conditions are satisfied by this formula. So we had made a good choice of terms. They satisfy the boundary conditions. We have chosen A, B, C, D in such a way that they satisfy the boundary condition. This, of course, satisfy the governing equation because they satisfy the biharmonic equation, and therefore from the uniqueness theorem we can say that this is indeed the solution. So once we plug this solution in, once we plug this A, B, C, D in, these would be the solutions to the stresses everywhere in the domain, including close to the hole. So now what we are going to do is we are going to look at, we know that far away from the hole, this sigma RR, sigma theta theta will tend to sigma 2 2, and this will tend to sigma 1 1. Okay, so let me see. So at theta equal to pi by 2, for example, theta equal to pi by 2, so you are here on this line, theta equal to pi by 2, your sigma theta theta is this, and that is same as sigma 1 1, theta equal to pi by 2. At theta equal to 0, you are here, and theta theta is this, and RR is this. So RR is equal to 1 1 and theta theta is equal to 2 2. So now what we see from the solution is that as R tends to 0, the remote stresses do converge to sigma 1 1 tending to sigma naught, and at theta equal to pi by 2 and r equal to a, if you put theta equal to pi by 2 and r equal to a, then sigma theta theta is equal to sigma 1, as I just showed. So if you put it here, then you will see that at r equal to a, this factor is going to be 2, and this factor is going to be 3 plus 1, 4 by 2, these two. And then the final stress intensity factor, this would lead to 3 sigma naught, and so what we have figured out just now is that if you apply a remote stress of sigma naught in the x direction close to the equator of the void, that is here and here, you are going to get at theta equal to pi by 2, you are going to get the maximum stress in the one direction, and that maximum stress will be 3 times the stress that you have applied the remote boundary. So the stress concentration factor at theta equal to pi by 2, r equal to a, is going to be 3 for this particular problem. So if you do, I did a finite element simulation for this, and this is how it looks like. So you have applied the sigma 1 1, and then the maximum, most red is 3. So you see that you have a stress concentration here and a stress concentration here, and that is of the order of 3 times what you have applied. The funny thing is that the stress concentration factor, that is 3, is not dependent on the size of the void. So no matter what the void is, as long as void radius is, as long as the plate is very large compared to the size of the void size does not matter. You always get a stress concentration factor of 3 at the equator. This is a very important problem. This is a very important result actually, and far away you see that this is sigma 1 1 by sigma naught is close to 1, because that's where nothing happens. There's no stress concentration. The stress concentration only takes place close to the equator of the void. Okay, so this is the first problem that we wanted to do. There's another problem that we'll do in the next class.